Welcome back to our course on artificial intelligence. In this unit, we delve into the intricate world of deep learning network training, the very process that empowers these complex networks to learn and excel. So, buckle up as we learn now about weights, biases, and cost functions. In our previous unit, we introduced deep learning as an artificial neural network with multiple hidden layers. Signals are forwarded through the network, passing through weighted sums and activation functions, ultimately progressing from the input to the output layer. What we'll unveil today is how they transform raw data into honed expertise, much like a student absorbing knowledge. In order to make the network learn, we first need to measure the performance of our model. To do this, we can calculate the error of loss over the different training samples for a given set of weights and biases. The average loss over all training data is called cost. A popular cost function is the mean squared error. The goal is to adjust the weights to find the minimum of the cost function. Gradient descent helps us adjust the weights and biases to minimize the cost. Let's start with a cost function with only one weight. The slope tells us if we have to go left or right to find the next minimum. To avoid overshooting, the step size gets smaller as the slope gets closer to zero. When we have many weights, we have a multidimensional cost function and we have to use the gradient instead of the slope. It's a vector pointing towards the direction of the steepest decline. The length of this vector indicates the steepness, but be careful. Often the found minimum is a local minimum instead of the desired global minimum. The cost can only be calculated for the output layer, which makes it difficult to determine the weights and biases for the hidden layers. To determine these weights and biases, the famous backpropagation method is used. First, the cost and the gradient is determined according to the predictions of the output layer. In our case, the output is too low, so we need to increase it. The weights and biases are adjusted according to the gradient. Now the output values of the previous layer can be changed to get the desired output by adjusting the weights and biases. This process is repeated until the input layer is reached. Calculating the cost for all data can be computationally very expensive. Therefore, we use stochastic gradient descent, where we train on random samples, so-called mini-batches of data only. In an iteration, the cost and gradient are computed for one of these mini-batches, and the weights and biases are updated. Each complete pass through the entire training data is then called an epoch. Observe this graph. The loss is steadily decreasing for the training data as the network learns. However, what happens to the test data loss? It doesn't further decrease after some epochs and converges against a constant value. As you can see from this example, training neural networks is often not an easy task. Common challenges are overfitting, as we saw in our example, high demand on computational resources, ideal parameter tuning, local minima of the gradient, or vanishing and exploding gradients. This phenomenon occurs when several very high or very small gradients of the layers are multiplied when using the chain rule for the backpropagation. And there you have it, the training process of a deep learning network demystified. Training is an iterative process of fine-tuning weights and biases based on cost functions that measure the error of the model. Gradient descent helps us to take steps in the direction of minimum error, guided by the calculated gradient. Backpropagation allows hidden layers to learn by propagating errors backwards. Stochastic gradient descent accelerates training by using smaller data batches. In the next chapter, we'll explore diverse network architecture and how they are trained for specific tasks. Until then, happy learning!